This is really cool. How are we all doing? Last talk of Coalesce. We were honestly banking on no one showing up and just being able to wing it. So this is really cool. It means a lot that you're all here when you could be enjoying the final beverage of the week. So thanks again for coming. Let's get into it. So we're here to talk today about a topic we're both super passionate about, and apparently other people are passionate about as well, and that is how to optimize your DBT project. If you're ever giving a talk and looking for a talk title, ChatGPT didn't do a bad job. All right, before diving in, maybe helpful to share a bit of background on ourselves. We're both data nerds. We spent our whole careers in the data space. I started my career at Capital One, worked there for a few years, and then most recently was at Shopify before starting Select, kind of wearing a variety of different data hats, all under the vague title of data scientist, whatever that is. And I'm joined here by Niall. He's also worked for a variety of different companies as a data engineer. And one of the things we've always both been really passionate about is efficient data modeling and data warehouse optimization. That actually led us to start our current company together. It's called Select. Select's a product that helps Snowflake customers and eventually other data warehousing tools monitor and optimize their usage. And since DBT and really any data transformation you do in the warehouse tends to represent a significant portion of our customers' workloads, a big focus of our product is helping people optimize DBT usage specifically. So we're super excited today to share all the things we've learned. We work with over 100 data teams on this and want to share all that back with you.
Okay. Oh, wow, I'm very loud.
You are, yeah. Quiet down.
There we go. Okay, so why should we invest in DBT optimization? First, and perhaps most importantly, an efficient DBT setup improves the developer experience, right? Which is a great thing. We've heard a lot about how DBT projects grow over time, and they can get quite unwieldy to work with. Optimizing the performance of those has a lot of benefits. And for the consumers of our projects, it also means lower latencies and faster insights. It's very use case dependent, but there are increasing needs for lower latency data in our downstream use cases. And finally, an optimized DBT project incurs lower cloud computing costs, which is quite a hot topic, and I imagine why a good few of you are here. Okay, so before we dive into the main agenda, it's worth just kind of it's a good meme. It's good to remind ourselves what DBT actually is within the context of optimization. Really, DBT just runs SQL queries, right? So optimizing DBT involves optimizing three things: DBT's configuration, the SQL that are in those models, and the configuration of the warehouse that the SQL is running in.
Right. So as Niall mentioned, DBT is ultimately executing SQL in your data warehouse and creating a bunch of different objects in it. So the first thing you need to do is understand how that data warehouse works, and also if you're focused on cost optimization, how are you actually build for that? Today, we're going to focus on Snowflake for a few reasons. It's one we're the most familiar with, tends to have the highest adoption we see in the market. But while we will focus on that, pretty much all the concepts we talk about will apply to the other modern data warehouses. If you're using BigQuery, Databricks, Redshift, I'm sorry, no, I'm just kidding. All those concepts will apply. So we're going to start by covering that. And once we have a good understanding of how that works, we're going to talk about low-hanging fruit. What are things you can do tomorrow if you're super keen, or next week to get immediate value without a lot of effort? We'll then talk about ways you can go about actually identifying optimization opportunities through adding observability, and then share, according to Niall, some juicy optimization tips and tricks. So things you can actually apply when it comes to trying to improve your performance or lower your costs. I guess two quick administrative items. So as mentioned, we're going to most likely use up all the time we have allotted because we're covering a lot. I think there's going to be something in here for everyone. This is not a beginner's talk. We're going to assume some foundational knowledge of DBT, so I apologize if you were not under that impression. I'm going to post the slides of this talk on our website probably sometimes next week. So there's some links where we have to dive deeper into certain topics, and you can check them out by accessing the slides after. And yeah, I think the other thing I'll mention is we're going to be around till like 4 today. So if people want to talk more specifically about any of this stuff, we would love to. All right, let's dive in, talk about Snowflake's architecture. So what makes Snowflake and all the other modern data warehouses really powerful, and what's kind of caused them to replace the incumbents that were used maybe 10, 20 years ago, is the fact that they have these separate independent layers of storage. And sorry, cool. They have all these different layers. So in Snowflake, the entry point for all queries is what's called the cloud services layer. This handles things like authentication, access control, query planning, so like the engine figures out how it's actually going to execute your query, and a bunch of other things like the global result cache. There's then the compute layer, which is the one most people care about. That's where your query actually gets processed. And then the final one is the storage layer. So Snowflake, in particular, runs on whatever cloud provider that you use. So it could run on Azure or AWS or GCP. So the data is stored in the storage service of that particular cloud. So if you're on AWS, it would be your data is in S3. The reason that's important is your data is not stored in the same place as where your compute's happening. So oftentimes pretty much all the time, the first step of a query is reading data from somewhere. So with these modern data warehouses, it has to go read that data over the network from cloud storage. So we're going to talk more about this later, but that can often be the most expensive step in your model. That can be the bottleneck, is that expensive reading. So that can often be a place to focus. So important to have that mental model in mind as you try and reason about why is this thing taking a long time to run. Cool. Let's talk about billing. So Snowflake in particular and all these modern data warehouses have usage-based billing models. You pay for what you use, which is great. You're billed for the compute you use or how much data you're storing. What's important to recognize here is from what we see with our customers on Snowflake, and I imagine is similar on the other data warehouses, is that compute typically makes the bulk of your bill. Let's call it 80 to 90%. So again, if you're in cost optimization mode, you need to be thinking that's where we need to focus. The other important thing to recognize with this is, with Snowflake in particular, you pay for the amount of time that the virtual warehouses that your queries are running on, how long they're up. So what can cause a virtual warehouse to stay up is your model takes a long time to run, or it's running really frequently. The frequency one is something that people often overlook. You can have a model that's really quick, but if it's executing a ton, that's going to add up. So those are the two different levers you kind of want to think about with your model, or your mental model, I should say. All right, let's talk about low-hanging fruit, things you can implement for a quick win.
Cool. All right, let's start with warehouses. So warehouse configuration. There are 3 parameters which are really important. First is the auto-suspend. So when you finish running a query, you obviously don't want that warehouse to keep running forever. You want it to shut down. The default auto-suspend for warehouses that you create through the UI is 5 minutes. That means that when the query finishes running, you're going to keep getting billed for another 5 minutes. We recommend setting this to 60 seconds. Next, ensure the minimum cluster count is set to 1. It probably already is, but just have a look through your warehouses. Every now and again, we come across a warehouse with a minimum cluster count of more than 1, which just means that you have idle compute. There's a bit of a theme here. And always start with an extra small warehouse. So for those of you not familiar, Snowflake's warehouse sizing comes in this kind of t-shirt size analogy. You start with an extra small, goes all the way to a 6XL, and doubles in resources and cost with each increment. An extra small is actually quite powerful. It's like 16 gigabytes of RAM, 8 threads. It's like a good laptop, and can usually cover kind of most of the requirements that you have in your account. On warehouses, consolidation is really, really important. We sometimes see accounts with tens, sometimes hundreds of warehouses. Having more and more warehouses, again, it's more idle time. As much as you can consolidate and maximize the number of queries that are running on a single warehouse, you're going to minimize that idle time and maximize the value you're getting per dollar that you're spending on the platform. So rather than separating by your kind of domain, like having a warehouse for marketing, one for finance, separate those warehouses by the workload requirements, like the data volumes and complexity. So in the case of dbt, we recommend just having one warehouse for each size that you'd use in your project. So most of those models can run on the extra small, as I mentioned, but then as you need to, you can run those more complex models on a warehouse that's more appropriate for their needs. More on dbt's configuration. 3 parameters that are really important. So the first is threads. By default, this is usually kind of 8, I think. and by the way, this is for both core and cloud, set this to actually quite a high value. What we don't want to have happen is that DBT is kind of bottlenecking itself because it's already running, say, 8 models, but the warehouse is ready to run even more queries. That's not a good thing. We actually want that bottleneck to be on the warehouse. We want queuing. That means that you're using the warehouse in a really effective way. So you can set this to 16. You could go higher if you like, to be honest, but that's going to make sure that you're getting maximum efficiency from the warehouse. Again, use an extra small by default. The warehouse that's set in your environment or profiles should be an extra small. Then you can use bigger warehouses as you need at the individual model level. And finally, this is a parameter which doesn't come up very much, but it's reuse connections. By default, this is set to false, and that means that DBT is going to create a new connection to Snowflake or any warehouse every time it starts a model. It's not massively significant, but it adds a few hundred milliseconds with every model as it has to do that kind of back and forth connection. And so, it's a free thing that will speed up your model, your project end to end. So definitely set it to true. As your project gets bigger over time, you'll start to have models which have been around for a while and maybe aren't used anymore. The kind of easiest way of identifying these is just by looking at access patterns and looking for tables which are no longer queried. It's actually a bit tricky with DBT because DBT itself is querying its own tables. So we only want to look at access patterns from non-DBT users. We have a blog post all about this, exactly how to do it with all of the SQL you need. So check it out. But deleting stuff you're no longer using, very effective way of reducing your costs. OK, so we've done the low-hanging fruit. You should definitely just go and do that. They don't take very much time. They'll probably save you some money. But next, let's go a bit deeper. So before we jump into hardcore optimization, we want to know what's actually driving our costs, right? You can't improve something that you're not measuring. So the best way to do that when it comes to DBT, and any workload, in fact, is with tagging. So you've got 2 options in DBT. There's the query comment config and also query tag. I'd recommend using query comment over tag because there's a limit to the number of characters you can get in there. And you can do this yourself. So things like the model name that's issuing the query, the environment that it's running in, the job ID, all things like that are really useful for attribution. Thankfully, you don't have to do it yourself, though. We have a package which is free to use, this DBT Snowflake monitoring package. We apply all of those tags for you, and there are a bunch of kind of convenience models in there to let you explore your cost in an easy way. So once you've set up that monitoring, the useful things to keep an eye on are the cost per model and also the cost across your different environments. So production scheduled runs, pull request testing, local development. And once you have that and you kind of understand where your costs are going, then you can start to think about, is it worth spending time optimizing this? Both in terms of, your value, how much are you worth, and how much is the other work that you could be doing worth as well. We don't want people to be spending hours optimizing a model that's only going to save you $5 a month. And here's an example of the kind of monitoring you can set up. So cost per model, ordered by descending, and also cost per environment that I was mentioning before. So this is actually like a screen from Select. You can achieve kind of lower but still helpful results in the BI tool. We review this once every week, looking for any issues that might have cropped up, and also if there are any models which are slowly over time getting more and more expensive to the point where it's worth us spending some time doing that optimization. And then we'll prioritize that work against other, really end-user valuable stuff to decide if it's worth doing. So it's as important to decide where you're focusing your efforts as where not to focus your effort is the real point here. And it's not always about costs, right? Sometimes we want to speed up the... another good meme, nice. Yeah.
We originally had a whole Taylor Swift themed presentation, but I didn't think it'd be funny, and I backtracked. I regret it now.
We should deny it. Sometimes you actually care about end-to-end runtime, right? Maybe you have a requirement for lower latency. In that case, check out the model timeline view. This is a screenshot from dbt Cloud. And what we can see here is a single model which is taking up a whole bunch of time with nothing else running in parallel. That represents the critical path in kind of Gantt terminology. And so if we can take, say, 10 minutes off of this model, the end-to-end runtime of the whole project is also going to go down by 10 minutes. So like a really high leverage use of optimization kind of resource to work on here. OK, let's move on to some orchestration and deployment practices. So for local development, it's likely that when you do a dbt run, you don't actually need to process your entire data set every single time. You're likely just kind of checking, is the SQL valid, and is the logic that's in there doing what I expect it to do? But you're not going to be looking at millions of rows, right? So quite a common practice we see is overriding the ref macro. You can do this in a number of ways. This is just a kind of high-level skeleton of what you might want to do. We are overriding the built-in ref and just wrapping a kind of subquery with this limit 1,000 clause. And so this model is just going to be way quicker than if we were running on the full data set. You'd probably want to add a bit more logic in here that kind of says, if target equals dev, then apply this, otherwise don't. But that gives you a kind of rough idea of the kind of thing you can achieve. When it comes to pull request testing, continuous deployment, CI, hopefully we're all using Slim CI. If you're not familiar with that, what it is, it's the kind of practice of only testing the things you've actually changed. State modified is the selector, which people have been using for a few years, but I think in the last year or so, there are actually some more specific selectors that you can use now. So state modified body, state modified configs. That's what we'd recommend to use as your selection criteria because it avoids rerunning a model just because you've changed like the markdown documentation. Who cares? You only want to test the model if you've actually changed the logic. And you can use the same principle of Slim CI in deployment too. So only full refreshing incremental models you've actually changed as opposed to the entire project. You can also use that same practice that I showed you of local development where you use a smaller data set in CI as well, so apply a limit. Obviously just be careful because you can end up in a situation where the first time that your models are running on representative data is in production, so you might want to be a bit more careful about how you generate those samples of data to make them representative and cover most of the edge cases you get in production. And finally, cancel redundant builds. Often people are making a small change, they git push it, and then they go, oh, I forgot to change the change log, do it again. You end up with a ton of queued builds where they don't actually matter anymore because you've superseded it. dbt Cloud does this automatically now, as we saw in the keynote earlier this week, which is great. If you're using GitHub Actions or other CI tools, they also support this cancel redundant build kind of feature. And lastly, there's a Snowflake parameter, which isn't just about dbt, this is kind of useful for everything, called abort detached query. By default, this is false, and what it means is if you run a query and then your session disconnects, Snowflake's going to run that query to completion regardless of whether you want the results or not. Apart from some maybe specific cases which you would know about, it's just worth setting this to true. Chances are, if you've disconnected, you've probably closed your laptop or someone's exited their BITL page, you don't actually care about executing that query anymore. So by setting this to true, Snowflake's going to cancel that query after a minute. Okay, so scheduling. We see a lot by default, I think everyone sets their project to run every single hour. And it sounds really obvious, but the impact of reducing the schedule is just so huge. If you run a model every hour that costs $10,000 a year, switching it to dailies, it's only going to be $500. It's very basic maths, but it makes such a huge difference. It's worth just considering a little bit what you can do here to reduce schedules, whether that's reducing the frequency at night or at the weekends. Again, 30% compute cost reduced just by stopping running at the weekend.
No one's checking your dashboard on a Sunday. I hope.
And if you have lower latency requirements, is there a way that you can synchronize your dbt runs with upstream data refreshes, which mean that you can actually reduce the schedule while still achieving lower latency data for your end users? Cool. On the scheduling front further, sometimes you have certain needs of your models which are lower latency, higher refresh. So maybe you have some kind of embedded analytics in your product where users are expecting to see lower latency data. But actually your finance team are just kind of doing month-to-month reporting and they don't need it to be so low latency. You can subsection your DAG so that you only run certain bits at an hourly frequency and other parts daily. You can use model selectors for this, whether you do it by folder or by tag. Or you can break your project out into several now with a multi-project ref that was just announced for dbt Cloud users. Okay, back to you, Ian.
Sweet. So let's talk about materialization strategies. dbt provides a bunch of different options out of the box. We're going to limit today's focus to the big three that we see out in the wild the most, view, table, and incremental. So let's start with when you should use a view. The simple mental model is that views should be used for very lightweight queries. So what could be an example of a lightweight query? Let's say you have a model that is just renaming columns. It's commonly done in a staging layer. That's a great use case for a view. Or if you're doing simple column calculations, so no crazy window functions, adding and subtracting, dividing things. Those are all great use cases for a view because data warehouses can very quickly, almost instantly, compute those extra columns on the fly. You don't need to persist them in storage. Another example would be models with lightweight joins. Let's say you have a giant fact table and you join it to kind of a small lookup dimension table. Again, data warehouses can do those joins very quickly on the fly. So good use cases for a view. So when you should not use a view and consider using one of the other strategies we talked about, anything that's really expensive or slow to compute and it's queried regularly, you don't want to repeat that expensive computation many times per day. Good example for materializing that as a table in your data warehouse. Or we're going to talk a bit more about concept of clustering, which has to do with like how the physical layout of your data once it's stored. But any model that has certain downstream use cases with specific filters that would benefit from clustering, in order to take advantage of those, you can't have it be a view. It'll have to be materialized as a physical table. OK, so if you're not using a view, how about table versus incremental? Generally speaking, we recommend using a table materialization wherever possible. And the reason for this is that they're simply the quickest to develop and the easiest to maintain. So incremental processing are typically much faster and more efficient. You only process the new data. You don't waste kind of computation reprocessing that historical data every time. But these can be generally much harder and more time-consuming to develop. You have to make a bunch of decisions, right? Think about how am I going to filter each of these CTEs correctly to only get the latest data, and what do I do about late arriving data? And then when it comes to maintaining those, if you add new columns, you have to make sure you're doing full refreshes or changing the logic. So we recommend starting with the table materialization, but there are good use cases for incremental. When Niall showed that model timeline view and the bottleneck, like that big model that is a critical path in your DAG, probably a good use case for incremental, so that can run quick. Or when you find that the table materialization will become very expensive and the cost of like your time to convert that or maintain it as an incremental model is much lower than the cost of the table materialization. So to ground that in an example, so our product runs on dbt, so we use dbt every day. We, as Niall mentioned, have a weekly ritual where we take a look at expensive dbt models or models that may have regressed in performance or cost. So we found that our top model that had bubbled up was using a table materialization, and it was making up over a fifth of all of our compute spend. This model was costing us over $8,000 a year, and we looked through the code and we're like, this will probably take like 2 hours to change to incremental. I unfortunately am not worth $4,000 per hour yet. Hopefully one day. So very obvious ROI. Like you spent the 2 hours, made the change, and you can see the cost and kind of average run cost go off a cliff. So very clear ROI. This is how we recommend you think about these types of things. Awesome. So we've covered the low-hanging fruit, the different configuration strategies on both the dbt side and your data warehouse side. Now let's cover some ways you can optimize the underlying queries in your data warehouse once you've figured out where to focus your time. So the first and arguably the most important query optimization technique in any data warehouse is this concept of query pruning. So if you reflect back on that architecture slide that I showed, and remember we have a separate compute and storage layer, you'll remember that that act of reading data from the remote storage will often be the most expensive step of your query. So wherever possible, you want to try and skip having to read data from storage. How can you do this? Through something called query pruning. So If we look at this example, we have the classic orders table, and we're filtering on a created at timestamp. If the data is laid out in a way that each kind of file is organized by date, we'll talk about how to achieve that in a second, this query in this hypothetical example can skip or eliminate reading a bunch of files because the data warehouse knows, oh, you're looking for everything after August. I know that all those other files don't contain any of that data, so I'm just not even going to bother reading them. This will make your query run way faster. So how can you enable your queries to prune? The big thing that you need is your table needs to be what we call well clustered. It needs to be kind of organized in a way that will enable those downstream queries to take advantage of that. So when should you think about clustering? It's really anytime you have a slow or expensive query. And the table you're running on top of, we typically say anything over a gigabyte. Why a gigabyte? For Snowflake specifically, the underlying files, which are called micropartitions, are typically around 16 megabytes. So with a gigabyte, you have a bunch of micropartitions, which means things could be eliminated. So that's kind of the rule of thumb there, over a gigabyte. And first and foremost, you're seeing slow queries or queries you want to optimize. Otherwise, spend your time on more valuable things. How do you decide which column you should cluster on? You want to look at columns that are frequently used in the where clauses of downstream queries. So you can figure this out by looking at the query history or the access history views to determine the usage patterns of your tables, or if you just know how people are using them, you can decide based on that. I'm not going to talk about all the different ways you can cluster, but we have a blog post on this. The key thing to look at with dbt is there's a cluster by configuration in your model, and that's what you can use to set the cluster key. In order to ensure you're taking advantage of clustering, I think all data warehouses come with a query profile, and you can use that to see how many files you're eliminating from scanning. So this is the Snowflake query profile. If we look at the bottom right here, you can see that it's scanning 5 out of the 3,200 micropartitions. So that's an example of very good query pruning. We always recommend checking this because there are corner cases where it can fail. So I showed an example before with like a where statement. That's kind of one of the most obvious cases where query pruning will kick in. You're explicitly filtering on a particular column with a value. Another example a lot of people don't know about that can be super helpful is with merge statements. So a merge statement is required for incremental models where you're not using a delete and upsert strategy. And what happens under the hood is Snowflake and other data warehouses will take your data that you're trying to update or add to the table and the existing big table that exists, and it has to join those together to figure out which record should I update and which one should I just add. So under the hood, there's a join involved, and as part of that join, it has to do a full scan of all of the data in that big table. So in this example, you can see that it has to scan pretty much all of the micropartitions because it's trying to figure out which record should we update. How can you make this go faster? Let's again use that example of this orders table that we're updating. Let's say we know it's clustered by the order date column. If you add that as an extra join condition in your merge statement, Snowflake can then kind of automatically say, what is the range of dates in this table, of this sample of orders that I'm updating? And it can automatically push that down as a filter into the target table. And you can see after doing that, just by adding that extra join condition, we're now only scanning 5 out of the 2,700 micropartitions. So a big reduction in data scanning and consequently a 60% reduction in runtime and most likely cost. How can you take advantage of this in dbt? That join condition that takes place during the merge statement is configured by this unique key parameter. So typically what we typically see is that's just the unique identifier, so like the order key in your table. But if you know your table is clustered by that order date column, you can add that in as an additional parameter, and you'll force that dynamic query pruning we talked about. Another one, filter early. Most of the time, Snowflake and other data warehouses will be very smart about if you have kind of a where statement way down in your SQL, it can know to push that up very early. There are specific scenarios where that can not happen automatically. For example, a qualify filter. I'm not going to go in depth on this one because I know we're running short on time, but essentially in this example, the qualify filter here only required information from one of the tables. But because qualify filters have to happen after the join, in this case, this customer had to join billions of records only to then filter out a bunch of them. So the solution here was to push this qualify statement with one of the tables up into a CTE, and that drops down from billions of records to millions, and then you're only pushing millions of rows, so orders of magnitude less through that expensive join step. So when in doubt, be very explicit and filter as early as possible. The final tip we'll leave you with is to simplify. 3 cases here, or 3 examples here. Avoid complex views. So as I mentioned, don't use a view when you have a very expensive query, because every time that view is referenced, it has to redo all those computations. Avoid chaining many views. So a chain view would be like a view that in turn references more views, that in turn reference more views, and the query quickly gets very ugly. I'll show you a fun one in a second. And the final one is have each query do less. Makes your life much easier, makes your coworkers' life much easier, and it decreases the chance of the query optimizer making the wrong decision with how to execute that query. So let's ground this in example. What could possibly go wrong with this simple model? It's just joining these two models together. As an example from one of our customers, we saw that this query was consistently taking over 45 minutes to run and frequently failing. Why was that happening? Deeply nested views. So those 2 models in turn reference views, which reference other views, and it just goes on and on and on. And I don't care how good your data warehouse is, it'll crap out when this happens. So very simple solution, simplify. All right, back to you now.
Cool. We've covered a lot. Here's a summary of where we've gone through. So understand your data warehouse's architecture and billing model. It's really important that you understand how you're getting billed to make a really good effort towards reducing those costs. Next, tackle the low-hanging fruit. Just do a quick audit of your account. Make sure there's nothing kind of crazy that's being set in the configuration. And next, measure your performance and your costs. You've got to understand where the costs are going in order to make a really kind of good effort at reducing them. So you can use our DBT package, create some dashboards for monitoring, some alerts, and implement just a ritual where you just regularly check your costs. And then get to optimization once you identify some good opportunities. And having worked on several optimization projects prior to Select, we found how time-consuming and slow this can be. So that's why we started Select. We provide automatic optimizations, all of this monitoring stuff, cost attribution, integrations. So if you are interested in learning more and having a kind of more managed solution to this, just reach out by the website and we can show you what we've got. Thank you so much for listening. We appreciate it's the end of the conference. We really appreciate it.
Yeah, thanks so much.
Yeah.